Okay, sorry I wasn't able to be there today, but I wanted to record this lecture about eigenvectors and eigenvalues. And in some sense, this was part of the focal point of what we were trying to do with focal point of the course, where we start looking at linear transformations from Rn to Rn and trying to resolve those linear transformations by using a coordinate change. All right, so let's go on this. In chapter 5, right, we start one of our main goals and is to better understand the linear transformations. And what we want to do is have the same domain and codomain, right, from Rn to Rn. And we talked about, on Wednesday, we talked about how in one dimension, all a linear transformation is a linear function of this form, where all you're doing is just multiplying by a constant, okay? And notice that the constant term, the plus 0, right, it's plus 0. There's no, plus b is plus 0. So sometimes we write this as y equals ax, right? For a linear function, y equals 3x, for example, is a linear transformation from R to R. Okay. And so one possible way to generalize this idea to multi-dimensions is to say, okay, let's have the linear transformation be taking x and multiplying that by a non-zero constant, or a constant. Take x2, multiply it by a constant, take x3, multiply it by a constant, x4, multiply it by a constant, and just do that for each coordinate. Okay, and that's one possible way to generalize things. And if I put it as a matrix vector product, all that's going on is I have a1 times x1, right? And so x1 times this column plus x2 times this column plus x3 times the next column and all the way through. And I just get this expression. All right. But notice that this is a diagonal matrix, and that's got to be one of our goals. And so if we can get something into diagonal form, that's great. That means we're understanding what's going on in each direction. Right? So the idea of eigenvectors is that while not all linear transformations we're able to make it look like what's above, we'd like to be able to resolve a linear operator. So what we mean by linear operator is something that starts at Rn and goes to Rn, okay, so that the dimensions of the domain and codomain are the same, right? So all we want to do is be able to try to see if we can resolve it into just scalar multiplication in different directions, but different directions may have different scalars, okay? And so what we want to do is we want to define a what we call an eigenvector. So what we're looking for is when t of this particular vector, right, is just going to be some sort of scalar multiplication of that vector, right? And what we do is it would be even better to get a basis of such vectors, because then we can create a coordinate system based on that. Okay. And we give these vectors a special name, and we call this, if t is a linear transformation Rn to Rn, we say a non-zero vector is an eigenvector of t, or an eigenvector of the corresponding standard matrix. If this is exactly what happens, is that when I'm plugging into t, or I multiply the vector by a, all I get out is a scalar multiple of the original vector. And so we call these eigenvectors, and we call the scalar multiple that's going on the eigenvalue. So this word eigen comes from the German. Okay, and we talked about how Zahlen comes from the German as well, for why we use z for integers. And it's just sort of saying sort of a characteristic. And so sometimes what you'll hear, sometimes people call these characteristic vectors or characteristic values. Okay. Traditionally, people call them eigenvectors and eigenvalues. Right? So here's an example. Right? I've got a matrix like this. A is, and then I give you this vector 1, 1, 1. and I ask, you know, show that 1, 1, 1 is an eigenvector of A, and then ask what the corresponding eigenvalue is. And so all we're doing on this is just saying, okay, we want to look at the product, we want to multiply A times 1, 1, 1. And so we go ahead and take this matrix vector product. When we do that, we get 2, 2, 2 as the answer. Okay. So 2, 2, 2 is just really 2 times the original vector, 1, 1, 1. Okay. So we have 1, 1, 1 as an eigenvector, right? Because when I multiply by the matrix, I just get a multiple of that factor. And the eigenvalue is whatever that multiple is. So in this case, we have the corresponding eigenvalue is 2. So this does not mean that A times U is equal to 2 times U for every vector in R3. This is actually just in the direction of V. Now, when I present this typically, I get the question, how did you know 1, 1, 1 works? And we will get into how you actually find these types of eigenvectors. But for now, just know that it works, or we can see that it works. But, you know, if I took 0, 1, 1, for instance, I made that a 0, 1, 1, well, what would you get? You'd get negative 2 plus 1, so that's going to be negative 1. You'd get 1. And then you get negative 3 plus 1, which is negative 2, which is not 0, 1, 1. Okay? So this doesn't happen all the time. These are very special vectors that correspond to this matrix. All right? All right. And so, for example, here, let's go ahead and look at another example here. So I have to take a look at this matrix A. And I want to, and I consider this triple of column vectors, show that B is a basis of R3, and that every element of B is an eigenvector, all right? And then we can take a look at the corresponding eigenvalues. So one, I can use the invertible matrix theorem to show this is a basis, all right? By taking a look at the reduced row echelon form, once I put all the basis elements into a matrix, I get the identity matrix. The invertible matrix theorem tells us that B is a basis of R3. Now again, remember, with a basis, when we did the invertible matrix theorem, we didn't have the term basis. But what the invertible matrix theorem is because it reduces to the identity matrix, the columns of B are both linearly independent and they generate. So that's what a basis is. So we get by the invertible matrix theorem, this is actually a basis. So show that B is a basis of R3. We've done that part. All right. Now we do like we did in the previous example and just check what happens when I multiply each basis element by A. I do that, I get negative 2, 2, 2, right, which is just 2 times my original vector. And so I have an eigenvalue of 2. Here I've got negative 1, 1, 1, so that's an eigenvector. All right, and here's my eigenvalue with corresponding eigenvalue 2. Okay. What about the other basis vectors? Well, let's take a look at 1, 0, 1. When we do that, we get 3, 0, 3. So, in this case, I've got 1, 0, 1, 3, 0, 3. I've got 3 times the original vector. All right. So, again, this is an eigenvector, but I have a different eigenvalue, right? So 1, 0, 1 is an eigenvector of A with corresponding eigenvalue 3. So this one had an eigenvalue of 2, this one had an eigenvalue of 3. What about this last one? All right, if I do that, I end up with 2, 1, 1, and I end up with a negative 2, negative 1, negative 1. Well, I've got a scalar multiple of the first one, right? It's just negative 1 times that. So 211 is also an eigenvalue of A, eigenvector of A, and with an eigenvalue -1. All right. So what do we have? We have a basis where each basis element is an eigenvector. All right. And they have different eigenvalues. This one has 2, this one has 3, this one has -1. So we can create bases of eigenvectors. All right. All right. So let's do a proof example. Actually, let me go back for a minute. So I've got a basis of eigenvectors, and one of the things we're going to be interested in a little bit later on is saying, okay, why don't we use this coordinate system, use this basis to form B coordinates in R3 when working with this matrix A, and what happens there. And we'll get into the details on that in section 5.3. Okay. So let's talk about a proof, right? Let's do a proof. Eigenvalues and eigenvectors, that's a very important definition. And so let's go through what a proof might look like in terms of dealing with with eigenvalues and eigenvectors. So let A and B be two n by n matrices. Let V be an eigenvector of A that's also an eigenvector of B. Prove that V is an eigenvector of A plus B. When we need to go back to the definition. How do I show something as an eigenvector of A plus B? I have to take that vector and multiply it by A plus B on the left and see if I get a multiple out. All right, but let's see what's given. Okay, since V is an eigenvector of both A and B, I can use the definition to say that AV is equal to some scalar times V. So think of that as a blob times V. And BV is a blob times V as well. Okay. Now they may be different values, so I want to denote these differently. So I'll call this one lambda 1, this one lambda 2. All right, for some scalars, lambda 1, lambda 2. All right. So now what do I need to do? I need to show that V is an eigenvector of A plus B. So what do? I multiply V by A plus B and see if I can get it to be a scalar times V, and blob times V. All right. So I go ahead and distribute. Well, now I've got a way to substitute this one in for AV and this one in for BV. And I get lambda 1 times V plus lambda 2 times V. I have the properties of a scalar multiplication. I can factor out the V. And what do I have? I've got a blob here, a scalar, times V. So if I start here, I say A plus B times V is a scalar times V. So that means it's an eigenvector of A plus B. All right. One key is that V is non-zero. Okay. And this gives that V is an eigenvector of A plus B with the corresponding eigenvalue. Well, what is a blob? Lambda 1 plus lambda 2. I'm done. I should point out that it is important in the definition, I forgot to emphasize this a little earlier, that an eigenvector is never the zero vector. Okay. The zero vector always works. If I plugged in the zero vector in here, A times a zero vector can be any scalar times the zero vector, right? It could be 358, it could be pi, it could be negative square root of 2. If this is a zero vector, that's always going to hold. And so what we're really interested in is, because we're looking for a basis or coordinate system, we're really interested in non-zero vectors when we do this. Right? So in the proof, notice that we say V is non-zero, right, here, as well as being non-zero. It's an important part of the definition. All right. So next, we consider how to verify that a given value is an eigenvalue for a particular matrix. Right. So let's take a look at this. Let lambda be an eigenvalue of an n by n matrix A. right? Then we can find a non-zero vector v such that AV is lambda v. So if you can find a non-zero vector of that form, then I've proven that lambda is an eigenvalue of A. The problem is finding a vector of that form just by guessing or just by observation is very hard to do. So how can we do this to find the actual vector v that's involved? Okay. So if I assume AV is equal to lambda v, as the definition requires of an eigenvalue, well, I can bring the lambda over to the other side of the equation, the lambda v, move this over and have AV minus lambda v is equal to 0. Now the problem is I can't factor out this v because otherwise I get A minus a scalar. It doesn't make any sense. So somehow I need to get, I want to be able to factor out this v, and I want a matrix here. So what I want to do is I want to put a 1 here, essentially, right? An identity matrix. And if I do that, then when I factor out the v, I get an expression involving matrices. All right. So that tells me that A minus lambda times the identity matrix, that's an n by n matrix now, times v is equal to 0. All right. But here's again where we talk about non-zero. What does that mean? Well, that means v is in the null space of this matrix, A minus lambda I. All right. So this null space has something that's not 0 in it because v is not 0. Right? Since the null space of A minus lambda I has a non-zero vector, that means, right, the null space, that means that A minus lambda I is not invertible. Okay, not invertible, that's important. That means any non-zero vector in the null space of A minus lambda I is an eigenvector of A with corresponding eigenvalue lambda. And what we'll do is we'll call if A is an eigenvalue of A, we call the null space of A minus lambda I, we call it the eigenspace. Now technically 0 is in this null space, but it's more than that. And so just make it a subspace, what we want to do is we want to add the 0. Okay? And we know it's a subspace because it's a null space, and all null spaces are subspaces. All right. So here's another example. All right, I give you A. I say show that -2 is an eigenvalue of A and find a basis for the corresponding eigenspace. All right, so we do that. What do? We take A minus -2, right, I3, and I compute the null space. But again, the negatives cancel, so I'm really taking the null space of A plus 2 times I3. If I do that, right, when I add 2 times I3, all I'm doing is adding 2 to each diagonal entry. All the numbers in black are going to be the original entries of A. And then because I'm solving for a null space, it's really just solving the corresponding homogeneous system. So I set that last column equal to 0. I do a reduce, I simplify it. I take its reduced row echelon form. And notice I've got a non-zero solution. All right, I've got a free variable here, right? X3 is a free variable. That means I have more than the 0 solution in there, and that will give me my eigenspace. It'll give me eigenvectors and eigenspace. So -2 is an eigenvalue. I've got the null space as t times this -3, -1, 1. Right? Remember, x3 is a parameter. I bring this over, it's -t. Bring that over, it's -3t. So I've got myself a eigenspace. I've got -2 as an eigenvalue of A. All right, and it asks for a basis of the corresponding eigenspace, which just means since this is dimension 1, all I do is take a non-zero vector in there, and so I can use -3, -1, 1 as a set by itself as a basis of this eigenspace. Notice if this were the identity matrix in 0, 0, 0, there would only be the 0 solution, and -2 would not be an eigenvalue. Okay. All right. So one can ask, are there any other eigenvalues of this A? I showed -2 is 1. I gave you the answer. How did I know it was -2? So how do you find eigenvalues? All right. And the key goes back, let's go back to this idea here. Is an eigenvalue is whenever A minus lambda times IN is non-invertible. Okay. Non-invertible. Okay, and so in chapter 3, we use the determinant to determine when a matrix is non-invertible. A square matrix, that is. All right, so if we go back to here, are there any other eigenvalues? If so, how do we find them? All right, so going back, lambda is an eigenvalue of A, then A minus lambda I3 is not invertible. And this is where we use the determinant in chapter 3. That means the determinant of A minus lambda I3 is 0. So here's a strategy. Let T be a variable and find all values of T such that the determinant of A minus T I3 is equal to 0. Right? Because if T has that value, then if T were negative, if T is -2, that's a value that works. That would be an eigenvalue. Once we find such a value, then we can take the null space of A minus lambda I3, which will be non-trivial, must contain an eigenvector associated with the eigenvalue lambda. Okay. So this is our primary strategy. This is part of why we needed the determinant, is to find these eigenvalues. And because of this, it's easier to find the eigenvalues than it is to find the eigenvectors. But once you have an eigenvalue, once you know you have an eigenvalue, then you can find the eigenvectors. Let's execute our strategy for the A that was in our example. So I take this determinant, right? Minus T times the identity. Again, all I do is subtract T off of each of the diagonal entries. I leave everything else the same. I go ahead and take that determinant. Typically, I put it in the calculator, all right? I can go ahead and do it by hand this way. I'll expand along the top row. Be careful the way this formatted. This negative sign goes with the 7 because we need to change the sign over here, right? It's plus, minus, plus as you go across the row. All right, I can go ahead then and take these 2 by 2 determinants and go ahead and simplify. All right. Keep going, I get this cubic equation. And what I need to do is I need to find the roots of this cubic polynomial. Okay. All right. And so you can do that. There are ways to do that on the calculator. We can do this, right? We can look at, we knew that T minus 2 is a root. So we can factor out the T minus 2. Factor theorem says T plus 2 is a factor. Okay. And when I do that, I'm left with this quadratic, T squared minus 7T plus 12. If I go ahead and factor that, that's quadratic. I need factors of 12 that add up to -7, -3, -4 work. So I've got a factorization of this cubic polynomial. So your eigenvalues are the roots of this cubic polynomial, right? So it's going to be, here's -2. So 3 is an eigenvalue and 4 is an eigenvalue. All right. So we claim negative 2, 3, 4. How do we verify that? Well, we need to find an eigenvector. We can find the corresponding null spaces. We already did this with negative 2. All right. And so now what we do is take 3. We go ahead and compute the null space of A minus 3i. I throw it into my matrix A, subtract 3 off of each of the diagonal entries. I get this matrix. I go ahead and take its reduced row echelon form. All right. And I've got one free variable. Notice that my free variable here is x2, not x3. x3 is equal to 0. All right. All right. Sorry for the interruption. Okay. But here we're computing the null space of A minus 3i. We go ahead and do that. We've got x2 as my free variable. x3 is equal to 0 here. So what do I get? I get that my null space is going to be x2 is t. That means x1 is also t because I bring it over to the other side. X3 is 0, so I get 1, 1, 0. This is non-zero, so that means that 3 is an eigenvalue of A. And for 4, we do the same thing, right? We take its reduced row echelon form. And here we have x3 as a free variable. X2 is equal to x3. X1 is equal to x3. And so you get 1, 1, 1 as a basis for the eigenspace. All right. And so that's the eigenspace for the eigenvalue lambda equals 4. And it turns out we can combine the above to get a basis for R3 that consists of eigenvectors resolving this linear transformation. So we can show that these 3 eigenvectors is actually a basis for R3. And each of the elements is an eigenvector. Okay. And so in particular, that describes everything we need to know about the linear transformation, because all I'm doing is if I take any vector in R3, I can write it as a linear combination of my basis vectors. T is a linear transformation. Well, so I have A times this. I can distribute the A, but A times B1 is negative 2 times B1. A times B2 is 3 times B2. A times B3 is 4 times B3. So what do you have? You have that T reflects and stretches by 2 in the B1 direction. It stretches by 3 in the B2 direction, and it stretches by 4 in the B3 direction. Right? And so that's all that linear transformation is doing. It's just stretching, compressing, reflecting in the different directions. Right? But I know what happens in each direction, and then I just put it all together, and I get what happens in all of R3. Right? All right. So it makes more sense to look at T and the B coordinates. Right. So in section 5.3, so we're going to work a little bit more on finding eigenvalues, finding the corresponding bases of the eigenspaces, and then looking at T and B coordinates. And so we'll talk a little bit more about that on Monday. So and we'll also see if you have any questions about this lecture. So I'm going to stop here. So enjoy your weekend.